Okay, so semiconductor diode. So just quickly from where we left off last week, so we looked into the phenomenon of thermionic emission, where we complete a circuit. Using a thermionic diode. So in a thermionic diode, there is actually no conductor inside. So there's actually a part of your circuit where there's actually no wire basically connecting. But instead, through using heat, through heating up a piece of metal and using certain polarities of negative and positive, we create free electrons in a vacuum, right? Which we call a cathode ray. We create free electrons that are able to cross over to the other side. So you free the electrons and then cross over to the opposite side, which has a positive charge, and therefore you are able to create a circuit. And not only that, this particular circuit can only move in one direction, right? Since we are using electrons, as we know, have a negative charge. And so it only works when the electrons are connected to the negative charge or negative terminal of a battery, so that the opposite side has a positive charge and the electrons are able to jump over because they're attracted to the positive charges in the circuit. All right, so that is one way of a diode. So as we talked about last week, it only works in one direction. And so today we'll be discussing more about this phenomenon of what we call a diode. So electrical components that only allow electricity to flow in one direction. Now there are many types of diodes. We talked about one last week, a thermionic diode. This week we'll be talking about semiconductor diodes, but there are also other types of diodes that we are not discussing. So keep that in mind when we talk about diodes. So we know that electricity, usually when we supply electricity in those big cable lines that you see outside, it is usually in the form of alternating current, right? So alternating current, as we know, is a type of electric current where it keeps on changing directions. So there's no real positive or negative side because it keeps changing. Which side is positive, which side is negative is actually always changing. Now, however, in everyday life, many electrical devices can only function with direct current. All right. If you think about it, let's say something like an electric motor, for example, a fan. You want the electricity to go in one direction because you only want the fan to spin in one direction. Right? If you use AC current on an object that requires DC power, either it will not really work properly, like the fan will start spinning, back and forth, or even worse, you might cause damage to those electrical devices. So before you use this AC current that we get from our power supply or from the sockets or from whatever, the alternating current has to be converted into a direct current, into a type of current that only moves in one direction. That's why almost every electric device that you see has some type of converter in it. Right? Your phone charger has a converter in it. Your laptop power adapter has a converter inside. Most things have a type of converter inside. So we can convert AC power into DC power using what's known as a semiconductor diode. So this is what a semiconductor diode looks like. Okay, we have this little black thing and a little silver thing. And if we were to draw it in a circuit, this is the symbol. So we have the anode and the cathode. And just remember that the triangle is pointing in the direction of the current, our conventional current, as we say. So, yes. So, yeah, we talked about this last week. And the semiconductor diode only allows electric current to join or to flow in one direction only, formed by joining a p-type semiconductor, sorry, P-type semiconductor and an N-type semiconductor to form a PN junction. Now, this is the part where your textbooks doesn't really explain a whole lot. I mean, what is a P-type conductor? What is a N-type semiconductor? So, for us to understand, first of all, obviously we know what conductors are. What's this? Why is this red thing up there? Never mind. So, first of all, we know what conductors are. Conductors, they conduct electricity. They easily create free electrons, which are then able to move around in a circuit. We also know what an insulator is. It's the opposite. There's not that many. Oh no, there are no free electrons. And therefore, it is unable to conduct an electric current. And we have semiconductors which are somewhere in between. Now, the most common type of semiconductor that we use is silicon. Silicon is normally used in computers and other electronic devices. Some other types of semiconductor is germanium. I think those two are the most common types. Okay, so usually when we're talking about P-type semiconductors and N-type, it's usually going to be silicon. Alright, so I'm going to read this first, and I'm going to explain to you what this is. So P-type semiconductors and N-type semiconductors are produced through a doping process in which foreign atoms are added into a lattice structure of a pure semiconductor. The majority charge carriers for P-type semiconductors are holes, whereas the majority charge carriers for N-type semiconductors are electrons. The hole acts as positive charge carriers. Alright, what does that mean? Alright, so let me get my face out of the way. So imagine silicon. Now in chemistry, you already learned about the different type of bonds between atoms, right? So you learn about ionic bonding and you learn about covalent bonding. So in ionic bonding, one atom releases the electron and the other atom receives an atom, and therefore both atoms become stable, right? Because they've filled up the outer shell, the valence shell. And in covalent bonding, if you remember, it's where different atoms, in order to get the required number of electrons, they share the electrons, right? So that should be chemistry form 4, I think. That's probably one of the first things you learn in chemistry in form 4. All right. So in pure silicon, as you can see in this picture, so in pure silicon, you can see it's a very stable structure, right? So each of the silicon atoms, you can see they are sharing electrons, and therefore every single silicon atom is in contact with 8 electrons. This is just an example here. So is in contact or is having 8 electrons, and it's sharing these electrons with the other atoms. And so what you get is, since they get to share with the other atoms, it's very stable. Now, pure silicon like this does not conduct electricity. Because that's wrong. Alright, this is not going to conduct electricity because there is no way for a free electron to happen. There are no free electrons here. There is no charge that's going to happen. So what we do is we do something called doping. Right? So when we do doping means we take this pure silicon and we add some other substance, some other foreign atoms. Alright, so we add foreign atoms into a lattice structure of pure silicon or of a pure semiconductor. So for example, here we have silicon. Now there are two possible things that might happen when you add a foreign substance. Alright, so for example, in what we call an N-type semiconductor, what happens is when you add a foreign substance, you add a foreign substance that has too many electrons. So as you can see here, now in this pink atom here, instead of being in contact with 8, it's being in contact with 9. So it's touching 9 electrons. Now, if you remember your chemistry, most things only need either 2 or 8 electrons to be stable. So now you have 9. You have an extra electron. So this extra electron doesn't need to be there. There's no space for it. And so, since you have an extra electron, since there's no space for it, it becomes, or it has the ability to become a free electron. Because they're gonna try and kick out this extra electron. They're going to try and get rid of it. And so in an N-type semiconductor, just remember that they have extra electrons. All right. Now, remember that an electron has a negative charge. That's why we say N-type, because the extra electrons create an extra or surplus negative charge. All right. Now, the opposite of an N-type semiconductor is what we call a P-type semiconductor. So, in a P-type semiconductor, we introduce an atom, or we introduce a substance that does not have enough electrons. Right? So, an N-type, we have an extra electron. In a P-type, we have 1 electron less. And so this creates what we call a hole, basically. So there's a space for another, there's a space for another electron, right? So this hole needs to be filled up. So they're going to try and find another electron to fill up this empty space. Now, because we are reducing the number of electrons, remember electron has a negative charge. If you take away a negative charge, or you reduce the amount of negative charge, meaning to say there are more positive charges. So these holes act or behave as a positive charge. So hopefully it's beginning to make sense what is actually happening here. So in these semiconductors, what we are creating here is we are creating a imbalance, basically an imbalance in charge. So in an N-type, we're adding negative charges by adding substances that have extra electrons. And in a P-type, we're adding positive charges by adding a substance creating holes, or, reducing the total number of electrons. All right. So maybe now that you've seen this, maybe now you're able to imagine, right? So a pure semiconductor is very stable, and this by itself is probably not going to conduct electricity. But when you have these things, you basically dope this semiconductors so that the electrons are a little bit unstable. You create this opportunity where, under certain circumstances, these electrons can actually move through the semiconductor. And so by doing this, by combining these two things, then we can create what is known as a p-n junction, right? So this is how a diode is created. So if you look at this picture now, you have the N-type. So N-type is on the right side. So the green ones are representing electrons, and the P-type are, the black circles are representing holes. So on one side you have extra electrons, and on the other side you have holes or positive charge. Now, when you bring these two together, what happens? So you can probably already imagine. So because negative is always naturally attracted to positive, what happens is some of the charges from one side will go over to the other. So what happens is this: instead of all the charges moving from one side to the other, only some of the charges actually go over to the other side. And then when the charges go over to the other side, it actually leaves behind holes. So now here we have in the middle an area that we call the depletion region. Okay, so you start from this, right? And they cross over because they are attracted to each other, but you leave a depletion region in the middle. So in this area here in the middle, basically now the electrons and the holes have been filled up. You are actually creating a sort of field here in the middle. So basically it's like this. This part here in the middle has become stable. But because this part in the middle has become stable, it is actually blocking the rest of the electrons from the N-type to go to the P-type. Because now this middle part is stable. The thicker this stable part becomes, the harder it is for the N-type from one side to go to the other. That's how it is. So you actually end up with a region where there's a slightly negative charge region and a slightly positive charge region. Now, in a typical diode, in a typical silicon diode, I should be specific, the potential difference, so there is actually a potential difference in this area, is 0.7 volts. That's important for later. Now, sometimes, if it's silicon, it's 0.7. If it's germanium, it's going to be 0.3 volts. Now, what happens? When we add now an electric current to this diode, what happens? So we connect the negative side to the N-type or the cathode, and we connect the positive side to the P-type or the anode. Alright, now look carefully at what happens. So when we connect the negative side to the N-type, so the negative side starts to release more electrons, right? Because there are electrons that are happening. When these electrons from the negative side of the battery reaches the N-type substance, now the N-type substance has even more negative, or there's even more electrons. Now because there are now more electrons on the N-type side, it now has enough energy to cross over this barrier to go to the other side. Right? Basically, the voltage is greater than the potential difference here. So basically, you need to have a stronger voltage than 0.7 in order to cross. That's what I'm saying. So now that you've added a battery, your voltage is higher than 0.7. You now have enough energy where this N-type can continue to move over to the P-type. And because it's going to continue giving more and more negative electrons, it can continue to flow and flow and flow. And so this, basically what happens is this depletion zone basically disappears and does not exist anymore. So we call this a forward bias. Meaning to say, because of the voltage, there's a forward bias, it's going to go forward in one direction. Now, if we try to turn it the other way, if we try to take this battery and we turn it the other way, what happens is you actually make the barrier or the depletion zone bigger. Because what happens? You connect the positive side with the negative, with the N-type. Remember, N-type is negative. You connect the positive charges with the negative terminal. And so instead of being attracted to each other, so instead of the negative electrons crossing over to the P-type, these negative electrons are being pulled towards the positive side. Remember, opposites attract. And same thing happens on the other side. These positively charged holes are being pulled basically towards the negative terminal of the battery. And so this causes the space in between this barrier, it's basically a barrier or this depletion region, to become wider. So, meaning to say, it will only work, or electricity can only flow if the N-type or the cathode is connected to the negative terminal. And P-type is connected to the positive terminal. If you reverse the battery, the opposite happens and no electricity can flow. And so that's basically a basic explanation of how a diode works. Now, your textbook doesn't go into this actually very deeply. And so it's likely that it's probably not going to come out in your exams. However, I think knowing this at the very least it will help you to understand better what's happening, because the textbook doesn't say what's happening. It just says this is what's happening, and I don't think that's really helpful when we were trying to learn about things. All right, so that's the concept of a diode. Now, this is basically, so it kind of shows you what's happening in the textbook, but it doesn't really it doesn't tell you why this happens. So forward bias circuit, so let me just read what it says. So in a forward bias circuit, the holes will move towards the N-type semiconductor while the electrons will move towards the P-type semiconductor. Right. And so the depletion layer becomes thinner or basically disappears. And so the junction voltage, so the voltage across the depletion layer decreases and the resistance of the diode becomes very small. And so the current passes through the diode. When a diode is reverse biased, the opposite happens. Instead of moving towards each other, they will move away from one another, and the depletion layer becomes thicker. And so because it becomes thicker, the resistance also increases. Therefore, when the resistance becomes high enough, the current basically stops flowing. So what is the use of a diode? So there are many uses of a diode. However, the main one that we will be discussing today is obviously, let me get my face up the way, the use of semiconductor diode and capacitor in the rectification of alternating current. So we were just mentioning how you cannot use AC power in most electronic devices. But we can use a diode to turn this AC current into a DC current. Because remember, since a diode only allows electricity to move or to flow in only one direction, we can use a diode to basically force the AC current to only go in one direction. So let's take a look at it. So photograph, so smartphones, you can't charge a smartphone with AC power. Okay, you can only charge it with a direct current. So the process of converting an alternating current or AC current into DC is known as rectification. So that's the term for it, rectification. So when I say rectify the current, that means I'm turning AC current into DC current. And so there are two types of rectification, which are known as half-wave rectification and full-wave rectification. So the word half-wave and full-wave comes from the shape of the current, or basically the shape of the current. So if we were to take an AC current and we put it into a cathode ray oscilloscope, it's a machine that shows us the current. What you'll see is that there are two half cycles. Basically, we have a positive cycle and a negative cycle. In other words, first the electricity flows in one direction, then it goes down, and then starts going to flow in the other direction. And so you get this sort of wavy thing. Okay, so flows one way, then flows the other way, flows one way, then the other way. Excuse me. So in half-wave rectification, what we do is we put one diode. So we put in one diode, and during the positive half cycle, so during one half of the cycle, the semiconductor is forward biased and allows current to flow through it. So it goes up. However, when the electricity tries to go the opposite direction, what does the diode do? The diode says stop. You're not allowed to go in the opposite direction. And so it's reverse biased and there is no current flow. So if we put it back in a cathode ray oscilloscope machine, this is what it looks like. So basically what we do is we take half of this wave. That's why we call it half-wave rectification. We only allow the positive half of the waves to go through, and the negative half we just say nope, cancel, don't move. You're not allowed to pass through. None shall pass. So This is half-wave rectification. The other type of rectification is full wave rectification. So I think you can imagine what full wave rectification means. So in full wave rectification, we rectify the whole, both half cycles or the whole cycle. Now, how do we do that? So for half wave rectification, it's simple. We can just use one diode. Now for full wave rectification, we use something called a bridge rectifier. So in a bridge rectifier, we are essentially using 4 diodes. So we use 4 diodes and we create this circuit right here in the picture. Okay. So basically what's happening is, okay, first, okay, I'll explain this later. It looks confusing when you first look at it. But the important thing is this is called a bridge rectifier and you need 4 diodes to make it work. Okay, so this arrangement allows a complete cycle of current flow in the same direction through the load R. In other words, by using 4 diodes like this, you can turn all of the AC or every single wave into a DC current. So the way it works is that every time there is a current, the current, starting from the battery, when the current flows, the current will flow and then it will reach a fork or basically a branch, right? And now in a normal circuit, it will just flow in both directions. It will go left and right. However, by using a diode, we can control the direction that this electricity flows. So take a look at the picture and I hope that you can trace it. So do your best to try and trace it. All right, so during the positive half cycle, we meaning to say you go moving in this direction. So you start from diode 1. All right, so you look at the arrows. So from diode 1, now why doesn't it go to diode 4, D4? It cannot because diode 4 is reverse bias. Diode 4 is acting as a gate. It says, stop, you're not allowed to go this way. Please go D1. All right, so the electricity has no choice but to go into D1. Okay, continuing from D1, again, there is actually a junction. It could either continue to the resistor or it could go into D3, but D3 says stop, you're not allowed to go there, please go in that direction. So it's kind of like traffic control, right? This is only a one-way road, they belong. All right, so it says stop, so D3 is blocking, so the electricity has no choice but to go and follow the rest of the circuit. And we come back to R and then we go back. All right, and it goes down and goes back up, and then back here again, same thing. You cannot go through D4, so it has to go through D2. So it goes through D2 and finally it goes back to D, and you end up coming back to the circle. Now look what happens here. When we change the direction of the charge, or with the negative half cycle, if you look at the second part, the lower part, the the current is still flowing in the same direction because the diodes, once again, these diodes are there to control the flow. So we're going in the opposite direction now. So it goes down and starting from here. Now you have a choice between D3 and D2. D2 says stop, you're not allowed to go down here. Please go down D3. So we go down D3. Okay, again, you cannot go up to D1. D1 says stop, one way only, please go forward, please proceed. And so no matter what direction you're flowing in, you end up with, no matter what direction the power supply is applying, there's always the same current that's flowing through the end at the resistor. So basically by creating different roads and controlling the directions, you can create a current that only flows in one direction. Pretty clever. So you end up where both halves of the cycle is made to flow in the same direction. So if you take a look at the waveform on a cathode ray oscilloscope, it will look like this. So instead of going in two different directions, so going up and down, both waves end up going in the same direction. So very interesting how they come up with ways to control the flow of electricity. And this is how computers and electronics work basically. By controlling the electricity flow into the different components and controlling how much and how little each component receives, right? That you can create a computer that does many different complicated and wonderful things. All right. Now, there is one problem though, right? Maybe you've noticed, excuse me. Now, there is a problem though. If I were to take this current, this waveform here, or even worse, if it's a half wave rectifier, and if I were to connect, say, a fan, you notice that the charge is not constant. It goes up, and goes to zero, and goes up, and then goes to zero. And it's really not a very, it's not a stable flow of electricity. It goes up and down, and keeps stopping. If I would try to connect a fan, probably the fan would not be able to function to its best because it's not a stable DC current. Same thing even with a full wave rectifier. You still do not have a stable current because it keeps on going back down to zero. So goes up, goes to zero, goes up, goes to zero, goes up, goes to zero. And so we need to use a capacitor to smooth out. So half wave and full wave rectifications produce a direct current which is not smooth. Therefore, a capacitor is used to smooth the current in a rectification circuit. So I don't know if you learned about capacitors in RBT. We used to learn about capacities in, well, it's not RBT, but we used to call it KHB, Kemahiran Hidup Bersepadu, which got replaced by RBT. But a capacitor, so the function of a capacitor is to smooth out the output. So you can see here in the circuit, we add a capacitor. So this letter C and two lines, that's the symbol for a capacitor. So what does this capacitor do? So basically, when the current is flowing, right? When the current is flowing, this capacitor will store up some of that energy. And when the so when the capacitor is flowing, the capacitor will store up or charge itself. So that when the electricity goes back to zero, what it does is that it will release some of that stored up energy. Basically, it will back up. So it will fill in the gaps, as you can see. So when the current goes to zero, the capacitor will back up and release some of it. And when the current comes back, it will charge up again. And when it goes back to zero, it will again back up and discharge some more. Okay, and if we use a full wave rectification output, then you get an even more stable, not completely flat, but much more stable, so much more usable DC current. So a capacitor basically fills up all the gaps in between. That's its job. So capacitor is connected in parallel to the load R. So you notice that it is connected in parallel like this, not in series. When the power supply is turned on, the output current becomes smooth. Okay, when the potential difference increases, the capacitor will be charged and energy is stored in the capacitor. So yeah, when there's current, the capacitor will charge itself up. And then when there's no current, the capacitor will release the capacitor will release this stored up charge to make up for the gaps in the current. And so you get a much smoother wave that looks like this. It's not completely smooth, as you can see. You can see the blue line. It still goes up and down a little bit, but it's much better than this one, because this one goes completely back to zero. This one, at least, it never goes back to zero. So this one, the difference between the top part and the low part is very small. And so And so, most electronic devices, electrical devices are designed to be able to handle some change in output. So most electrical devices will be able to handle this, but not this. This will not work. This will work. So that is basically everything about diodes from your textbook. So any questions? We have some time left, so I would like to continue into the discussion about transistors. I don't think I'll finish it today, because there's actually a lot to explain, and even if I finish the slides today, we do need to look at some demonstrations, or at least some good graphics to at least help you better understand. But any questions for this part before I go and discuss a little bit about transistors? So does that mean you understand everything or you understand nothing? Yeah, I always get nervous when there are no questions, because I wonder, does that mean do you understand everything or you understand nothing? It's either one of those two. Anyway, if there are no questions at the moment, then I will continue to transistors. So we took a look at what a diode is and how a diode functions. Now, if you understand how a diode works, that helps you to understand how transistors work. It does work on a similar, not exactly the same, but there's a lot of similarities with how transistors and diodes work. I will just go. I won't go too much into detail, because in all honesty, your textbook does not go into detail on transistors. However, I think this is just my opinion. I think your textbook is skipping too much of the basics on transistors, which makes it a little bit difficult to understand what it's saying about transistors. But I will just briefly discuss transistors. So a transistor is an electronic component with three terminals. We have the emitter, the base, and the collector. So it looks like this. Now you may have seen, if you ever tried to open up a computer motherboard or any other sort of electronic device, you may have seen these components before. Now, three terminals, emitter, base, and collector. Right? So emitter supplies charge carriers to the collector. B is a thin layer in the middle of a transistor to control the flow of charge carriers from emitter to collector. This is very important. All right, and I will go into this later. And collector C receives charge carriers from the emitter. So basically, the way a transistor works is that an electric current will flow through C and E. You can see it in this picture. There's an arrow that's showing that electricity will go from C to B. But there is a condition. The condition is, for electricity to flow from C to E, B must also receive an electric current. If the base does not receive an electric current, then even if you connect C and E to a circuit, it will not flow. Okay, that's the basic function of a transistor, all right? So there are two types of transistors, NPN transistor and PNP transistor. So we understand what NPN is and what PNP is, right? You take a semiconductor and you dope it to create either an N-type or a P-type semiconductor. Now, instead of having two layers, we have three layers, right? So either an NPN or a PNP. The difference is the direction that the current will flow, right? So from NPN transistor, it'll flow from the collector to the emitter. For a PNP, it will flow from the emitter to the collector. But other than that, the way it functions is still the same. If there is no charge flowing through B, then no electricity is going to happen through E and C. So the way B functions as the gatekeeper in a circuit. B is saying, if I don't get electricity, you're not getting electricity either. Basically. If I don't get electricity, if I don't get any current, nobody gets any current. Right? How does that happen? We don't really have, we won't have much time to go into depth on that. However, you can try and figure this out. Okay, this is something that you can go home and figure out. You know how a PN junction works, right? Now try to imagine if you add a third part, so NPN or PNP, and try to imagine how the electrons would work out. Okay, that should help you to understand. Basically, what is happening. Basically, a transistor is a diode with an extra layer. Think of it like that. That'll help you to understand. And so, because it's a diode with an extra layer, as long as the base part is receiving electricity, the rest of the thing can really receive electricity. Alright, so transistors are widely used in digital circuits like computers. What are the characteristics of transistor circuits? Okay, and how are NPN and PNP transistors connected in a circuit? So how do they work and how do we use it? So the first thing that you need to understand is that a transistor circuit consists of two main parts. We have a base circuit and we have a collector circuit. All right. So if we go back to this thing, right? Remember that there is the base part and the circuit and the collector part. So electricity is obviously flowing from collector to emitter, but there's also a circuit for B. So if the base circuit or if B is not getting any electric current, then no electric current can go from C to E either. So something like this. So if you look at these pictures, so we have an example for NPN transistor and PNP transistors. Let me get my face out of the way. There is basically two main circuits in this picture. Excuse me. They are all connected to each other, by the way. All right. So there's one circuit that basically controls the current that goes from the base, as flowing through the base. And there's another circuit that is going through the collector, right? And by the way, both base and collector, they both flow through the emitter side. All right. So take a look at this. Take a look at this picture. This is in your textbook. It's a little bit long. We will go through this several times. Probably next week I'll go through this again. We'll see. Now, let's read what it says. When switch is open, bulb L1 does not light up as the circuit is incomplete and the base current LB is 0. Alright, so if we leave this switch open, obviously, since the circuit is not complete, there is no flow of electricity. Now, it actually looks like, where's L1? Right, so L1 is not going to light up, obviously, because it's not a complete circuit. L1 is here. L1 is this light here. So obviously this part is not a complete circuit, so it should not light up. However, L2, the second light bulb, also does not light up. Which is, if you think about it, normally should be able to light up. Why? Because this other half of the circuit is actually complete. However, since B, the base, is not receiving any current, it stops the the other half of the collector circuit, I should say, it stops the collector circuit from flowing. So this B, this base here, is basically saying I'm not getting any current, so you're also not allowed to get any current. Right? So now, when the switch is closed, right, bulb 1 is dim because RB has a high resistance. Right, so if we close the switch now we have a resistor here, so L1 is not going to light up very brightly. And so the current of the base circuit is going to be pretty small. Okay, however, in the other circuit, there's no resistor. And now that the base point is receiving some current, it is now saying, okay, now that I'm getting some current, I will allow current to flow from the collector to the emitter. And so the other light also lights up. All right. And so what is happening here is that by giving the base a little bit of current, it allows a lot of current to flow in the collector circuit. And this is the important thing about a transistor. This is how a transistor works. A transistor works as a... Okay, I'm going to continue. The transistor works as a switch, basically. Right? It basically works as a complicated switch, in which instead of using a button as a switch, we use electricity to control. We're using electricity to control electricity. That's basically what we're doing. Okay? If the base circuit gets no electricity, nothing can flow through the collector circuit. If the base circuit gets a little bit of electricity current, the collector circuit can have will now allow to flow an even bigger current. Right? This is why it says there the base current can control the flow of the collector current. This enables the transistor to act as a switch. The resistance at the base circuit is large to limit the base current so that the transistor will not become too hot and burn. So basically, this transistor, the base side should not receive a big current. Usually, it should only receive a small current so that it doesn't burn out quickly. Now, the collector side, the collector circuit, it can be a large current. So, how is this useful? All right. So now thinking, okay, why go through all of that? Why should we make such a complicated switch? Can't ada switch. So why not just use a simple switch? Well, of course you could do that. However, it doesn't. With a switch, you only have two choices. It's either on or off, right? It's either on or off. With a transistor, you have control. So the way a transistor works is that the more current is flowing through the base, the more current that the base will allow to go from collector to emitter. Right? Basically, think of it like this. The base point or the base circuit is the gate, right? You put a little bit of electricity in it, the gate opens a little bit. You put a lot of electric current through it, it opens up completely. And so by using that concept, we can control how much current we want flowing in the collector circuit. So if we want a little bit of current in the collector circuit, we give the transistor or we give the base just a small current. Okay, we want to give it more current in the collector circuit. We also give the base circuit more current. That is how a transistor can function as a current amplifier. Right? So basically an amplifier works where you can make the volume go up and down. Basically, we're using a transistor. So when the volume is low, we're giving a small current to the base circuit, and it only lets a small amount in the collector circuit. When we turn the volume knob, we increase the amount of current that the base receives. The collector circuit also receives a larger, or it also not receives, but the base then will allow a larger current to flow through the collector circuit. Right? So that's the thing. You with a transistor, you can control exactly how much current you want to flow. Unlike a switch, it's either on or off. Alright, so in a transistor circuit, the power supply or battery will supply a fixed potential difference. Okay, the transistor requires a potential difference V BE. The BE should be small, it should be down there, which is more than the minimum voltage for it to function. To acquire this small potential difference, a potential divider circuit can be used. So we have to add a resistor because a transistor you need about you only need a small voltage, about 0.7 for it to open up fully. And so we usually add resistors. Right, so in the potential divider method, two resistors with resistance R1 and R2 should be connected in series with a power supply as shown in figure 5.70. As the same current is flowing through both the resistors, the relationship between the voltage and the resistance is shown by the following equation. Voltage out equals R2 over R1 plus R2 times voltage in. Okay. Basically, this sentence here is a good summary of the whole thing. The current does not flow in the collector circuit unless there is a current flowing in the base circuit. Right? So we can also use this means that we can also use other things to use this transistor as an automatic switch. For example, we could use a light dependent resistor. So a light dependent resistor is a type of resistor. Its resistance change with the intensity of light. The LDR is high when the light intensity is low and vice versa. So the more light it gets, the lower the resistance. And so we could put it in a component like this. We put the LDR in the base circuit. So we use the LDR to control how much current is in the base circuit. So for example, when it gets dark, when it gets bright, it has a low resistance, and so electricity will flow through it. And since electricity flows through it, it will not flow through the base collector. It will not flow through the base circuit, but instead it will take a shortcut here. And so, because there's no current flowing through the base, there's no electricity flowing through the collector circuit. But when it turns dark, and suddenly, when it turns dark, suddenly this LDR has a high resistance. And so because it has a high resistance, it's easier for the electricity to flow through the base current through the base circuit. And so it goes through the base circuit instead. And then you end up with a completed circuit and the light automatically turns on. You can do the same thing with a thermistor in a heat-controlled switch. Same idea, right? You place a thermistor there and you control the resistance. So when the temperature goes up, the resistance becomes low. And when the temperature goes down, so basically the temperature goes up and down, also changes the overall resistance, which also changes the amount of electricity that goes through the base circuit. And by changing the amount of electricity that goes through the base circuit, the current will go up and down, and the heater will also change in response to the changes in electricity. And so you can automatically control the temperature of a house or of a room. All right, that is basically a very short explanation of transistors. All right, there is a lot more we can talk about transistors, and I think we'll probably want to spend a little bit more time on transistors because especially with these circuits, we need to take some time in understanding where exactly is everything flowing, right? Where is everything flowing so that you know how it looks like. Once you understand how everything is flowing, everything else becomes easier actually. I'll send you a link to some videos that are very helpful in understanding how transistors work. Okay, so I'm not going to ask you to do formative practice 5.3 today because I still want to review transistors next week. But I will ask you to do formative practice 5.2. So diodes are, I think, much easier. They're quite straightforward compared to transistors, right? For diodes, basically, you need to understand what is forward bias and what is reverse bias. This part here is actually all bonus. How exactly this happens this year, this is all bonus. The important thing is that you know what forward bias is and what what reverse bias is, and what are the uses of semiconductor diodes and how to use a capacitor, right? So for today, go ahead and do 5.2, formative practice 5.2. Next week, after we discuss transistors in more detail, then we can do 5.3. Yeah. All right. So, any questions either about diodes or about transistors? Or if there's something that you do not understand, please let me know, because then I can decide what I need to focus on for the next class. Or anything that you're curious about. Let me just stop the recording first.